again. Friday, December the 8th, 2023. I wanted to get started on problem 10e. We'll just call this function h of z. That's difficult to read. I see two ways to start working on this problem, and I've no idea that we might be able to solve it using any of those methods, but that's the two ideas I've got. The one is to repeat the work that we did in 10c, I think, working practically on this function, working practically on this function. And there we need to go through the action of all gammas, of course in gamma naught of n squared, but all gammas in the special linear group over z. And they are generated like t to something, s, t to something, s, etc., t to something, and then maybe an s. And this t doesn't matter because E2 has period 1. So we can discard that. So we actually have to compute the action of st to the 8th and then maybe finishing off with s. So that might be one way. We have the formula in 10b that might come in handy, or an analogous formula coming in handily. Maybe we can use it on this. I guess it was 10b, and then the other one will be t to a nth, and then another block. Yeah, so we might be able to do this. Not a n, some ai. And then use the same block. So we might be able to come somewhere using all this. I don't look particularly hopeful, but the other way doesn't seem too great for me anyway. And we start rewriting E2 of here. It's some constant, never mind which it is. Is it 4 divided by p squared? I don't know. Oops. 1 divided by z plus j divided by n squared. Now what am I doing? This is ridiculous. That's the z value. So that has to be multiplied by m and then plus n squared. And then this n we take outside. I will just write it as minus. N z plus j times m plus n minus second. That gives nmz plus jm plus nn. And now this must be compared to g 0.j modulo n 2. This doesn't quite work because we have a weird order of addition. But I actually think that for each m, so for each m we make the sum over n, and that gives the same no matter how it's translated. So it actually should be the same. Good. So that was a first step in this direction. This is actually D, so it should be C again. And here we see that this should be invariant with respect to gamma naught of n. But actually all the theory, we are not at all sure about that. All this, the theory we have in the section on dk only holds if k is larger than or equal to 3. So we have to look at the transformation formulas again in case k is 2. So I think I'll start doing this. It seems to be more promising. We were going to check a transformation of this. They perform this calculation in the book. I'll just write it up. Doesn't that mean that we are just changing the order of addition here? I think it does. This being just a constant term under the summation of n. Now what I don't like is that this is... Oh no, it's not the contrary of what happens. because we have the transformation formula for the sum as well. So that seems, I believe I can get through this. I would like to know the constant. Or rather, we must of course, it's not all integers we go through here, it's only a few of them. I'll have to think a little about how to change the order of the sums. Maybe we should from scratch make our own transformation formula, like they did in the in section 2 of chapter 3. That might be interesting. Or maybe we can use the transformation function formula for E2. I just think a little about that. That will require a little work. What I'll do is that I'll repeat the trick from developing this transformation formula. For E2. I think this was the one. I think I have to use the same trick, but some over less fewer terms. I'll see if I can go do something that way, but I will do it off the screen, I think. I did have a feeling I was not very bright today. That turned out to be true. You see, here we have 2 terms, and then 2 by 2 terms, that gives 4. Altogether 6 terms, so I'm missing out 2 terms here. My God. And of course, when n divides c, then this is equivalent to naught modulo c, no, modulo n. And this, when we sum over n, again, it's just a translation of a fixed translation, so it gives the same as just summing over dj modulo n plus a constant times n. This is constant, and there's a little reordering here by dn. I don't think that matters. I haven't proven it yet, but it's one of the things I might have to look at when we reorder a series, a series that only converges conditionally. Then when we want to change the sum, there needs to be no limit to the distance between the terms we rearrange. And here they are all within n squared, which means that the reordering, the sections being reordered are bounded. So I think we might be able to prove that this gives just put a question mark by it. let's assume that for the time being and then see how the terms rearrange and what happens all together. We have to split, of course, considering one when that's in the multiplicative group, and then all the others and since we have n divides this, so this is equivalent to unity modulo n, and that means that d actually lies in this guy. As well as a, which we're not going to use. So I'll just write up that we assume that is, we assume gamma lies in gamma naught of course it's n squared, but we haven't been applying this yet. That may come. All right. Well, I think that's as far as I can get today. Sunday morning, December the 10th. I very much doubted that this could be true. And so I checked it out later. And unfortunately, I'd not say unfortunately, it turned out I did perform a morph. This is still almost recognizable as an n, but here it's morphed into an n, which means that this doesn't hold. The sequence of addition is really warped, and that means I'm back to my proposition A here, working directly on this. The first thing we might try is to, I just get the idea that we might write this my idea was first to make the Q expansions. What we should do was to make a general transformation of this and see what happens, and then hope that we don't end in something as weird as this, or as intractable. Let's take each of these atoms and see how they transform. And can we do anything about that? It does not morph that into an A. And what do we do now? Well, we must trot on. This we call alpha. Well, an idea is needed, so it didn't get very much longer. Now it's Monday, December 12th. I haven't had much time working on the problem, but this morning I got an idea that I just wanted to report. Now this seems quite intractable as it stands, but I got the idea to transform the content of E2, and just to show the idea, we will just transform E2 of Z and then a matrix in gamma, and then I will change this expression to be something depending on E2 and not more E2 of Z itself, not more complicated. And we should make, to illustrate the idea, let's say 13 and 8, and then try to complement them to a matrix of determinant unity. And now this gives a function 8z minus 3 minus second, and then this. And then we try to minimize the coefficient to Z, and here we can just subtract 1. So that gives 5Z minus 2. And then we use the transformation formula to get something with E2. No, we do not do that yet. First we subtract 1. And now we use the transformation formula. And we add twice the denominator. And now we add 2 times the, we could add 1 time the, and then get unity. Let's see what that leads to. That was my idea. Actually, I would like to here add add 2. We'll just do that first. So I feel I made a mistake because this didn't give something I expected. I expected the coefficient to Z to be unity. But that was my idea, to make such a series of transformations, and then we might be able to make a general formula for what comes out, or say something in general about it, and then apply it to these more complex. So I'll be working on ideas along this path the following days. Good morning, December 25th, Christmas Day. I gave up on problem 10e. It would take, I estimated, a fortnight before knowing whether I could actually carry through the problem or not by the strategy I devised. So I decided to read the hint. And that seems as an extremely easy way to come through the problem, and it was quite a surprise to me. So it said, start by showing that, and then the product of the delta functions, or the translation of the delta functions, are in here. Well, I did study the proof of problem 17b, and then it all became clear to me how to solve it. First, we need to show that the translations satisfy a condition of formula 3.8. So if we have a function has the right format, infinity. And how is it with this transformation? So it's delta of AZ plus B divided by ZZ. We have been through this. So we can see that first we transform Z, and afterwards, oh, it's a plus, we translate, and that means that it's delta, and then we first operate on it by gamma, and afterwards by the translation, Tj, where the translation is given by this. And we have actually been through a similar argument, but I just want to do the details again. So I defined the gamma matrix. We can't use gamma in Mabel because that's the, I don't know which constant, it's some constant, or maybe it's a gamma function, I don't know. Or maybe there is a constant called gamma. Let's see if that's the case. It is, I forgot that. I even forget what number it is now, though I do recognize the digits. Well, so here we have the translation. And to have integer entries, we multiply it by n. And then, of course, it has determinant n squared. And the point is that doing row operations, we can get a naught here. And doing row operations is equivalent to multiplying by t to nth, n being some integer, and then exchanging rows. That's s. That changes sign, of course, of the bottom row, but that doesn't change anything. And that way we can get a guy. We make them smaller and smaller because when we subtracted the nth division number of times, then the numeric value becomes less than the numeric value of this, and then so it's less than this, and then we can exchange rows and repeat. So eventually, first it will become the common denominator of the two, and then it vanishes and becomes naught. One can do it simpler than that. It becoming smaller until it's naught, then it will be constant. So that means we can get a naught here, and all the operations, row operations, they come in front, and that just gives a matrix in gamma. So that means that it can be written as some matrix in, we call it G, times a matrix of the form A is not a good number, X, Y, Z, and G is delta is invariant with respect to G. And this is just a translation, and it has determinant n squared. So the worst we can get is n squared down here and unity up here. So, and that implies that we get an expansion in Qn squared, which was what we should by 3/8. So that was the expansion has the right form. Then we shall show that the product is invariant under gamma naught n squared. I plan to do it on the next page, but let's just do it here. Product, they use J from naught to n minus 1, delta, now we have the form of the translation, and the point is the formula on the bottom of page 128. I computed it in Maple. So we have the we take one factor and then operate on it with G, and that is equivalent to operating on delta with this matrix, and then we multiply by t of minus some j, the translation minus j, and this is the formula on the bottom of page 128. Now C lies in gamma naught n squared. Now gamma lies in gamma naught n squared, and that means that n squared divides C. Oops. And that means this is an integer, this is an integer, this is an integer. So this is the guilty party. So the point is that for each I, or was it each j, I just have to look. I would have chosen I, but I think the book has j here. Yeah, j. For each j, we can pick an I, a value of I, so that this is divisible by n. And that means that all the entries are integers. And of course, the determinant of this guy is unity. That can be seen directly, by the way. And then it lies in gamma. Of course, if j is naught, I becomes naught trivially. But otherwise, we can always choose. There's only one solution in we have A and D lie in the multiplicative group. And that means that working in the ring, there is one and only one solution, and that means there is one and only one solution. And this interval, that's silly. There we go. So it's a one-to-one operation from j to I. So how can we write it? Yes, first we operate on this with a matrix gamma. And it's a factor, well, what should we call it? I don't know what it's called, this. 12 for each of these, there are n, so it's actually 12n. Yeah, that's what it says. This was the translation j, gamma, and 12 on each factor. Oh, so this is we are on each factor here, so we only need the 12. On each factor, right. And now the point is that each one can be written as sum G depending on J times G. I'll just write it. So it was G J Ti minus first equals sum G there we go. I depending on J, and we come through all the ones, and then it's invariant under Gj. And this is just the translations, so that's the same product as the first one. So that proves that the product, and of course it's a Spitzen form, cusp form, because all the deltas are, or even just one of them is delta naught, but they all are. All right. And now we can take the next part. Define f to be this, and this is a modular cusp form of order 12n. So is this. So the one divided with the other is a modular function of order naught, just a modular function of gamma naught n. That means this holds. So it's just a question of dividing this guy. So we didn't need all this. I prepared doing some work here, which we could do on the other page. So we have f of gamma z equals f of z. So we take the derivative. We take the logarithmic derivative. We have already had that in section 1, that this equals zz plus d minus squared. That's where the that it comes that it's of order 2, the result. So let's take the delta function itself. And now what was that? Z times 1 minus q to the nth. Was it just that? I'll just pause and look. Yeah, it was to the 24th, and then a constant 2 pi to 12th, which I tend to forget. We'll put it on the end, at the end. logarithmic derivative. I think we have done this before. My. Yeah, this is 2pi. Oh, it's a minus, even a minus. Oh, it's I plus 1, so it would say n to the ith plus n, that's I n plus 1, but this sums from n equals naught, so this is from n equals unity to I equals unity to infinity, and this is also from 1 to unity. From 1 to infinity, and then we collect all the terms ending in a given m. Oh, where were the I? It's up here. And that's all the divisors. So that's just the sum of divisors. That was the worst sigma of the day. Sigma 1 of m q to m. And we have been through this before, that this is 24 times this is minus E2, and then the unity, which will cancel out. So we are basically through now. My God. Now, I'll just do the details. and that was E2 of Z, except for unity here. So that's minus 2pi, that gives plus 2pi. And of course, all the translations will give the same with the translations in here. And that means that we have from delta, I'll just write it up. It was delta to nth divided by the product of all the translations. So log dip, the logarithmic derivative, so we get n halves, or the constants, they cancel because there are n adding and n subtracting. And then we get minus 2pi E2 of Z times n minus the sum of the translated E2s. That was really a tough problem. Now I think I've solved it, or rather solved and solved. I didn't solve it, but I was able to do the things from the hint. I don't think I would have ever gotten the idea. I might have discovered it by accident later, but I would never, starting with this, have gotten the idea that we had to look at the delta function.